Good morning, ladies and gentlemen. Here we are after the semester break. Let me tell you something. It looks I worked too much in the first half of the semester. Eventually, I wanted to miss one lecture in the end of the semester, but it looks like I gave it. Correct me if I'm wrong. Also, let us check if you kind of followed the lectures. Did I give the lecture number 7 about homemade quantum mechanics? Who can remember this? Please put, as usual, your questions and answers to the chat. Yeah, Timo recalls something. Anybody else? It was Johnson effect in lecture number 6. And there was a combination of Coulomb blockade and Josephson effect in lecture number 7. Right, good. So that corresponds to what I recall. So initially, I didn't plan this lecture in the end of the semester, but somehow I forgotten about not playing. I gave it. So to summarize, today we go on with lecture number 8. And we will have yet another change of topic. Right. So we have started with scattering approach. You remember, we've been looking at interference. Lecture number 2, lecture number 3, we've been looking at quasi-classical approaches as a situation when there are many conducting channels and Ohm's law holds. Right. First lecture was circuit theory, when we dealt with quantum waves which obey Ohm's law. Fifth lecture was Coulomb blockade. Sixth lecture was superconductivity. And in the lecture number 7, we combine these two to get homemade quantum mechanics, to get Josephson realizations of qubits. We will talk about qubits later. Now I want to return to scattering, right? I want to return to scattering. Now we understand more or less what is a classical transport. We've been looking at it. And I would like to zoom on quantum corrections to classical transport. All right. We partially touched this topic when we were talking about interference, but that was from the point of view of quantum transport. Now we will try to understand it starting from classical transport. So quantum corrections. We've been talking about phenomenology of these corrections, how to measure it, how to understand them. And there will be 2 corrections which have names, perhaps not very comprehensive. We will talk about weak localization and universal conductance fluctuations. Right, experimentally they are seen in magnetic field dependence of conductance, usually very simple and consistent experiments which have been done for ages. We look again at experiments we have shortly looked at in lecture number 2. Was it 2? Yes, it was 2. We've got to some advanced things, and actually we will understand the role of spin in localization. We understand how to express these quantum corrections in terms of trajectory loops, and it can be seen as return probability. Then, just to give you a notion that the same answer or the same physical phenomenon can be described in many ways, we will talk about a random matrix theory and how to understand these corrections in terms of random matrix theory. We will learn some things about random matrices in the course of that. Time allows, I will talk a little bit about strong localizations, about situations where electronic states in strongly disordered metals are in fact completely localized. There are no electrons lying around. They kind of bounce between some barriers all the time. Good. That corresponds to these sections of the book. Fine. So let us go on. Sometimes I have a difficulty in Zoom just with simple keyboard shortcuts. Oh, no, it's not the case. Right. Let us understand what are these corrections. Corrections to what first, and corrections and why would they occur? Right. Let us talk about classical conductor with many channels. And many channels, as we remember, is reflected in conductance of this conductor, right? Each channel contributes a GQ to the conductance. So for many channels, we have conductance much bigger than conductance quotient. Right. There's still quantum interference going on in this conductor, because the electrons which traverse this conductor are still waves, are still quantum mechanical waves. They are very complex because of multiple scatterings, because of they have to live in many channels, but they're still waves. As such, there must be some interference contribution to quantum transport. And there are ways to make it experimentally accessible. We've been talking about it in lecture 2 in the context of Aronoff-Bohm effect. Magnetic field changes interference patterns among different electron trajectories, and looking at magnetic field dependence of same conductance, one can review this interference correction. Good. Let me tell you the answer, and this is kind of fundamental answer, easy to remember. These interference corrections appear at the scale of one channel conductance. So corrections are always of the order of GQ. Kind of from many n channels, one channel contributes to these fluctuations. That's good, but in practical experiments, it's rather difficult to keep coherence over the whole conductor. Quantum mechanical phase is forgotten at some length scale, which also depends on temperature. We will talk more about this in the last lecture of this course, but let me just now take it for granted that coherence for a large sample, let me sketch a large two-dimensional sample, for instance, 1 millimeter distance, will only persist at a certain scale that can be characterized with length. It can also be characterized with a time which is required for electron to go to diffuse through this region. Okay, so there's a coherence which is conserved at this energy space scale. All right, so how one can treat this realistic situation incoherent classical conductor? Well, we could just separate it into pieces, each piece being of the order of this phase breaking length. So that can be seen as each incoherent conductor, even very big one, can be seen as a collection of smaller coherent conductors. Right. In addition, their size can be tuned by magnetic field, again, because magnetic field destroys interference patterns. One could think that the size of the conductors is affected by magnetic field. Right. And each conductor from this collection has interference contribution, which is of the order of GQ. So that's why interference effects can be seen in large incoherent conductors. Right. These effects, weak localization in particular, has been studied quite a bit about 30, 40 years ago. And it was by the time revolution, first quantum revolution in condensed matter physics. Right, people have been much excited of seeing quantum effects in something which looked entirely classical, which was very far from atomic systems. That's why they even forged a special term, mesoscopics, which means roughly quantum mechanics adds the scales which are measured in between atomic scale and human scale. Right. This science still persists because eventually any experiment made at low temperature, one can see this interference corrections. You can characterize your samples nearby. You can use it for some applications. Mostly I will be talking about extended diffuse conductors. So if you just take a piece of materials, the impurity side, the scattering propagation of electrons is diffusive. So there will be no design in our nanostructure. We just take a piece of metal, a wire, something like that. Good. That's what that's what I need to outline in very beginning. So, did it go well? Do we understand what we will discuss today? Fine, good. We experimentally mostly conductance is assessed, but I need to, I want to mention that it can be seen in any transport phenomenon. For instance, there are quantum corrections to noise, current noise, which is measured can be measured in nanostructures. There are quantum corrections to transfer properties in the presence of superconductivity as well. Um, Quantum corrections to wave reflection in extended diffusion conductors. So, but historically, and because it's easy, the simplest physical measurement is actually measurement of conductance. We will also mainly talk about conductance. Right, so weak localization. That's, if you just follow the title, it looks a little bit confusing perhaps. Localization is a property of something to be localized to persist on infinite volume. So localization should not do anything with a transport, which is about electron transfer. Electrons, if there's transport, electrons are not localized. And what does it mean weak? If it's localized, it is localized. If it's not localized, very confusing. But anyway, as confusing words somehow might become emotional, and they really become the names of physical phenomena. So let us define it in more precise terms. What is drift localization? It's a quantum correction to conductance, which is averaged over formally identical nanostructures. That strange definition, it assumes that we have an ability to stamp nanostructures. We make nanostructures with large conductance and we make many of them, but we could not control, as we discussed, phase shifts. We could not control configurations of impurities. So these conductances will fluctuate a bit. So we average over them and get a number which is supposed to be different from classical value. One can figure out what is this number, for instance, applied by a magnetic field to each nanostructure and averaging the difference between the high and low magnetic field. All right, as I promised, all interference effects are of the order of conductance quantum. But of course, nobody, in practice, nobody uses this time-consuming and unreliable method of making formally identical nanostructures. The way to average is to let the nature or whatever the device to average is. So if one can just take a large incoherent sample, right, we will have, in fact, a plenty of coherent conductors in series. Each has weak localization correction, and measuring the total conductance, one gets it, one gets a correction. Here, I just put it into formulas. So we have, that's for total conductance of n incoherent conductance in series, the quantum correction to a sample which encompasses n incoherent conductors, you just divide it by n. So it means that your sample doesn't have to be, since conductance can be measured very precisely, usually there is no problem with large n. Good. So let us see.
Sorry, can I ask you a question?
Yeah, sure.
These nanostructures you're talking about, are they the same you drew in the previous slide that compose a bigger incoherent mesoscopic structure? Or are they different devices? Or
in this case, we just take, say, a wire, lone metallic wire. There's not much structure except one has to make contacts to this wire. What I mean by this picture, a very long wire is not coherent. Quantum mechanics does not persist over the whole length of the wire. But it can be separated into pieces where quantum coherence is preserved. And each such piece is a coherent conductor, can be regarded as a nanostructure. That's why I put those in series.
okay, I see. But isn't then this division a bit arbitrary? Because I mean, I can see that it makes sense to consider quantum coherence effects inside a certain coherence length, but then why do you choose this separation and not maybe, I don't know, like from the half of the first segment to the half of the second segment? Is my question clear?
This is just a cartoon, right? So in reality, one finds formulas which have the same dependence on the length, on the number of connectors. So it is just to understand how the quantum correction can persist even for incoherent conductor.
Okay, thank you.
Fine. And what I wanted to say, it is automatically average. There are fluctuations in each conductor, but if one takes many of them in series, well, we will see it in the next page, then the effect of fluctuations is self-averaged.
Can I also ask a question?
Yeah, sure. Eventually, I prefer to if you put it on the chat, but still there are not many of you. All right, let's go on.
Okay, so if you use a long wire to represent the incoherent sample, is n just the length of the wire, or how do you define n in that case?
Yeah, n is a number of these incoherent conductors. So if one knows the length at which coherence is broken, one takes the whole the total length and divide it by length at which coherence is broken. All right. Good. So this is one manifestation, weak localization. Let me talk about other one. Let me talk about universal conductance fluctuations. This is half confusing. This is indeed conductance fluctuations. Right. Let us first look at the let's start with assuming that we can stamp identical nanostructures. Then, as I said, although we want to make it identical, there are always fluctuations in phase shifts in impurity configurations, and they're not precisely identical. And the conductance changes from sample to sample a little bit, right? In most practical examples, due to fabrication errors, and I have a short story about this, I will tell it later. But there is also a quantum limit of these fluctuations. And again, it turns out that that the variance of these fluctuations is defined by conductance quantum. So it is of the same order as average correction. So if one looks at it in a big incoherent sample, again, we take a sample which is larger than coherence length, we separate it into pieces, and we look at the fluctuations of the totals. Here I gave you a derivation, and that's how to see fluctuations, these fluctuations, in terms of fluctuation of resistance of the whole sample. As you see, it's inversely proportional to the number of coherent conductors. So it's inversely proportional to the length cube of the sample. But since the conductance measurements can be done very accurately, one can see and trace this contribution for realistic samples. Again, now we don't, in this situation, we don't measure the fluctuations of a single conductor. We measure some average result, but the average result also fluctuates. Right. Perhaps there's not enough motivation. Well, who cares about fluctuations, right? The fluctuations always kind of assume something unimportant to be disregarded. Just to motivate you, let me tell you a short story about how important fluctuations of conductance can be. Right. The story took place approximately the same time as first experiments about weak localization have commenced. Right. There was that time it was a Cold War competition, a very bad competition between kind of almost mirror symmetric partners, United States of America and the Soviet Union. Good. And the problem, they have to make kind of similar devices by different means and using different technologies and different levels of technology. For instance, one would have to make a control center for a missile. Electronics at that time was rather big. So perhaps you remember TV sets from your grandmother. It was really a big box. Something like that one has to manufacture to compete in Cold War. And when you make a complex piece of electronics of the part of this complexity, you make it from parts. Basically, these parts are small resistances, and at least resistors, capacitors are components of that. And ideally, as a matter of design, you need to, for instance, make 10,000 of resistances of identical resistance, but it never works. Never works. There is some fluctuation. And the whole piece of electronics which you made of these elements only works, well, just to give a number, if the distribution is of the order of 1%, narrow distribution. Good, but to make resistors with little fluctuations, you need advanced technology, and sometimes you miss it. So again, just to give an example, Soviet technology was not so sophisticated, and if they wanted to make the same resistors, the distribution would be like, say, 10 times bigger. Fine. So who can play for Russians and give me and guess how did they deal with the problem? So you've got elements, you assemble something working from these elements, and the fluctuations of elements are such that this is not supposed to work. But you need that. Your bosses need to get this complex piece of electronics. Has somebody an idea or perhaps read about this? Yeah, resistance in series, it's a good move, but in fact, it is difficult to make it in electronics, where each piece kind of has its own function. One could make parallel circuits for such electronics, but this is too complex. It was not a way. It was much simpler way. Okay, let me tell you, it's kind of from the point of view of physics, it's a strikingly simple trick. They made these electronics from round resistors, and they put it on a test site. They put it on a test site, they check if this total assembled piece worked. And owing to this distribution, only 1% of the pieces actually worked, owing to statistical fluctuations. So they knew how to use probability theory to achieve the goal. Simple trick. Although the simplest trick, there is a price tag, of course, for the same, to achieve the same result, they had to do it like 100 times more work. Labor costs were cheaper than in the United States, of course. The total level of life was much more modest. So perhaps effectively it was only 10 times more expensive. But that kind of made the game. In fact, at some stage, the Cold War and arms race became too expensive for Soviet Union, and it has actually collapsed. All because of small fluctuations of resistance in individual resistors. Fine, that was the story. We have to go on. Let me, I have already told several times about magnetic field dependence. Let me recall what we have discussed in lecture number 2. That time we had two beam splitters. We have considered different trajectories. And we look how the interference of these trajectories is affected by flux, which has been put through the loop between these beam splitters. And actually, although we didn't name it like this, I believe we can have analogies of weak localization and universal conductance fluctuations in this for these trajectories. First, universal conductance fluctuations. It's very simple. There are simple trajectories which traverse the sample taken other ways, different ways. And interference between this phase shift between these trajectories picks up magnetic field. But also it picks up dynamical phases, phases which depend on potential distribution in the nanostructure, and they're also random for random trajectories. That's why this gives us fluctuations. They're affected by magnetic field, but they supposed to vanish if we average over dynamical phase. There is, however, a trick which concerns this particular trajectories. As you see, these trajectories make a loop, and the direction of this loop, they only differ by the direction of going over the loop, which is counterclockwise in this case, and clockwise for trajectory D. And when you look at interference of these trajectories, dynamical phase does not enter, so the interference of these two particular trajectories is affected by magnetic field only. That's why they survive averaging over dynamical phases. Fine. From this one can have a notion how magnetic field affects affects projector affects the conductance in a regular sample without obvious loops. Here we don't have predefined paths, but anyway, the trajectories in bulk metal would make loops anyhow. These loops come in different in different sizes depending on the trajectory. All sizes are present. Right, and if one applies such a magnetic field by the interference is destroyed for trajectories which have loop sizes such that the flux through the loop is bigger or comparable with flux quantum. Yeah? That's what I put here. So this is estimation of the area covered by trajectory times magnetic field. When it is of the order of flux quantum, interference at this trajectory, at this loop size, is destroyed by a magnetic field. So fun enough, changing magnetic field, we change space scale at which interference happens. Space scales can be related to time. If one recalls that there's diffusive transport, so diffusion coefficient defines your time related to this. Good. I shall stress that it's diffusion, so trajectories are complex. Trajectories are rather like this. But anyway, one can talk about the spread of this trajectory, although it's very irregular. That's how magnetic field dependence comes about, right? There are no predefined passes as we studied in Aronoff-Bohm effect. Nevertheless, Aronoff-Bohm effect happens in each trajectory for each loop size, and changing magnetic field, one can kind of scan through the loops of different sizes. All right, let us look at experiments which are made for weak localization. That one I have already shown to you. It was about conductance of metallic cylinders with a small hole. So a magnetic field penetrated the hole, and one could see quasi-periodic signal like this, with a period corresponding to flux quantum. So that's why how weak localization has been discovered. But again, for observing weak localization, one doesn't have to have this geometries. One doesn't have to make cylinders, which is difficult, but could just measure the conductance of a large 2D sample versus magnetic field. All right. That's what they did, actually, for characterization of the sample. And they do see quite some pictures. So they apply gate voltage, modifying the properties of 2D gas, and they could see a variety of behaviors. There is a peak of conductance, or there is a dip with double peak, or some fancy behavior, which they use to characterize what's going on in the material. Right. With some luck, we will explain this picture. But to do this, we need to kind of get qualitative reasoning about this weak localization. Let us see. Experiment on universal conductance fluctuations. Right. I believe I also showed you in lecture number 2. That was pioneering experiment. So since the samples required for weak localization are larger, it has been observed earlier. That was pioneering experiment to see conductance fluctuations. They made a small metallic ring. They made a loop to have a signature periodicity of fluctuations with respect to flags. But as you see, they didn't see regular periodicities. Since their fluctuations, they've been kind of noisy with respect to magnetic fields. There are many trajectories contributed to the conductance, and I believe, all right, well, one can see it from the value of conductance, of the resistance. It was like 100 ohm, and conductance quantum, inverse conductance quantum, it's like 300 ohms, sorry, 10,000 ohm. So the number of conductance in this, of conducting channels in the structure was about 100. And as you see, it's roughly there were fluctuations of the order of 1%, which corresponded to estimation to that fluctuations are of the order of conductance quantum in size. All right, so although the curves look like random functions of magnetic field, which is natural, there were also some periods which one could extract by doing Fourier analysis of these trajectories as a function of magnetic field. Fine. So this is an observation of conductance fluctuations. One can do many things. One can do magnetic field dependence, temperature dependence, actually quenching it if temperature is sufficiently large. Then coherence length becomes very short, shorter than the sample size. All right, that was experiment about conductance fluctuations. So let me make a break at this point. Let's make it 8 minutes. So we talk again at 9:40. Let me stop the recording. Our lecture. Let me tell you something which is a little bit strange, counterintuitive, nevertheless, which is observed in this quantum correction business. A localization and anti-localization. If we, and why localization is weak, if electron spin is not important for traversing when electron traverses, if it doesn't change its spin or change it just a little bit, the sign of the correction corresponds to smaller conductance. That's why it is eventually called localization. So electrons have tendency to be localized. That makes the transport more difficult, smaller conductance. And strangely enough, if one takes spin into account, one can get opposite sign of the change, anti-localization. What is a simple model to see that? Let us imagine two trajectories for electron to go from point 1 to point 2. Let us talk about amplitudes corresponding to these trajectories. If spin is not important, if spin is not affected by traversing the sample, these trajectories, these amplitudes do not depend on spin actually, right? So for both spin directions, the amplitude is precisely the same. Well, if the propagation scattering is such that spin can be changed, then there is a spin-dependent contribution to this amplitude. Right, for trajectories like this, the spin contribution is eventually opposite because of different clockwise direction. All right, and what one can do about this? Let us compute as in double slit experiment the total probability to go from point 1 to point 2 as affected by flux. Right, so it's a contribution, it's a sum of amplitudes we should take, and we need to square it. Okay, this probability is given, has a term which is not affected by flux. Let's call it classical probability, does not depend on interference, and a piece which does depend on interference. Okay. Right. And the algebra of this Pauli matrices is such that for classical probability, a contribution of spin comes as plus. It's natural, so there are also, we add probabilities, there are some probabilities to come with spin change. Yeah, they're also positive. But if one looks at interference, one observes different sign of spin contribution. So the sign of interference correction can be changed if this spin-dependent amplitude is sufficiently strong. Good. So with or without spin, we can have different signs of this correction. Let us try to get a formula for this. Let's try to figure out what are these corrections, how we can do this. Roughly, we need to find the ratio of trajectories with these self-intersecting loops to the total number of trajectories. So I put it symbolically here. Here it's a sign of division, the ratio of numbers of the two. First of all, it seems senseless problem because intuitively it is this has to be zero, right? If trajectories are infinitesimally thin, this crossing intersection of trajectories would never happen. However, one has to take into account that trajectories have a final width, well, of the order of electron wavelengths. That makes it already quantum effect, right? So if they come to each other at the size smaller than electron wavelengths, one can regard it as a loop. Fine. if you take this into account, we can come up with estimation which contains classical quantity. Namely, one could just start somewhere in the beginning of the loop and follow the diffusive trajectory of electron. So the number of the loops of made by propagation of electron by different times is given by classical return probability to come back to the same point as a result of diffusion. Here we have return probability. All right. We need to sum up our all trajectories, which is equivalent to integration over all possible times of going around the loop. This also density of states that comes due to the fact that one has to take into account finite thickness of the trajectory. That gives a factor which is inversely proportional to density of states. Right. Besides that, there is a variety of factors. Let me look at it. Let me start from the end. First of all, quantum mechanical phase can be broken during this trip. So long trajectories eventually do not contribute to the interference. This is taken into account by this factor. So if time is bigger than a typical time scale of interference loss, these trajectories do not contribute. Same with magnetic field. As we discussed, magnetic field affects interference and cancels interference. So there's also some time related to magnetic field, which suppresses trajectories which are longer, which propagate during a bigger time. Then about spin localization and anti-localization. There is a term which is not affected by spin, and there is a term which is affected by spin. And there is another time scale, a time scale at which electron, in cause of scattering, does change spin orbit time. So it also enters here, and due to this localization, anti-localization, these terms come with different signs. Fine. So we have a working formula to estimate weak localization correction. And the kind of heart of this formula is a completely classical quantity, return probability. Which we have to take in the same points, right? Why there's a factor of 3 for spin coherence time? All right, how can I answer this question? There are 3 Pauli matrices presenting 2 by 2 matrix, and there's only one matrix which does not depend on spin. That this is responsible for these factors. Spin contribution from Pauli matrix is quantitated sufficiently long times, and this persists. Right. So probability, how one could find this probability in general? Well, this probability obeys diffusion equation. So here I put the diffusion equation. So second order derivatives, time derivatives, and there is a source. So one puts in the time moment 0 a particle to the point r prime. It propagates, and the solution of diffusion equation gives you a probability per unit volume concentration to be at any point r. Good. Then to utilize this formula, we just have to put r equal r prime. So it's a practical way to assess weak localization correction. Let us see what we can do with this. First of all, let us have very crude estimation, which eventually recovers the answer which we have already. Let us consider nanostructure of a finite volume. And then diffusion trajectory, we start at point R, and there is a diffusion trajectory which persists for some time before it leaves this nanostructure. All right, so how we can estimate this return probability? It is just 1 over volume for times not exceeding escape time. Now we can implement the formula we have, density of states, integration over time, probability. So what we have, density of states and volume will give us level spacing in nanostructure. And integration over time will give us inverse of escape rate. But this, I believe we have shown it already, or didn't we? Okay, let me put a statement first. This is eventually for any nanostructure can be presented as a ratio of conductance quantum and conductance. I don't remember whether we discussed this relation. Does somebody remember how to show this? No? Okay. That's simple. Let us consider now structure on the left. Suppose we have some tunnel barrier, and there are levels in the nanostructure. So there's continuous spectrum outside, and those are field levels. Discrete levels in the nanostructure. I'll put them here. These levels are field. They're a bit high energy. So the difference is voltage applied. And there's, of course, empty levels. How can I put it? Yeah, with different color. Let us estimate the current through this system. Right. From one hand, this current is voltage applied times conductance, right? From the other hand, current is elementary charge times number of transfers per unit time. Rate of the transfer is this escape rate, and number of levels from which electrons can transfer. What is this? It is the voltage divided by this level spacing. Right. Yeah, if gamma escape is time, eventually I miss H bar over here. Yeah, sorry, H bar. I'm not really accustomed to write H bar. Yeah, but this if there's energy, that has to be energy here, so rate times H bar. Fine. Now we just cancel voltage in both parts since it's the same current estimated in 2 ways, and we end up with gamma escape divided by delta S G divided by P squared over H bar, which is conductance quantum. Okay, done. Right, with this, we recover our estimation. So, in fact, it depends only on total conductance of the structure. Good, that was very root estimation and root answer. Let me give more sophisticated answer for 2D. I put it on the next page. Yeah, here we have it. It's for 2 dimensions. So it is, for instance, situation 2-dimensional electron gas. Right, and in this case, the return probability can be obtained from solution of differential equation in 2 dimensions, and it is inversely proportional to time. Now, remember, we need to integrate it over time, this probability. So we have integrals like dt divided by t, which give rise to logarithms. These logarithms have to be cut at some very short time, a time of scattering at the impurities, and all time scales, spin orbit, magnetic field, decoherence time, they enter the answer. So this is already a pretty good fitting formula for results in 1 dimension. All right, let me come back to this experiment. And eventually this experiment was made to demonstrate that spin-orbit interactions, the strengths of spin-orbit interaction can be tuned in these nanostructures. As we see in all traces something which happens at this particular scale of magnetic field. For this particular scale of magnetic field, the time related to the magnetic field is of the order of the phasing time. And in addition, there is a third time scale, spin orbit, which can be either smaller than the phasing or bigger than the phasing. And if it is smaller than the phasing, we have a dip. We change we change gate voltage. We make spin orbit interaction more intense, and we get to this. So as we see, we have a change of sign at magnetic field because it's either localization or anti-localization. And from the position of the wiggle, where peak is transferred into dip, we can estimate spin orbit time. That was the reason, the goal of this experiment. Fine, that was weak localization. And let me change the gears completely. We have understood it on the language of electrons, trajectories. Let me try an alternative language, rather abstract language. Let me talk about random matrix theory. We will talk about random matrix theory twice. First, in the context of transmission eigenvalues. Second, in the context of electronic levels in a quantum dot. The kind of power of random matrix theory is that it can be applied just to any matrices you can imagine. So for transport, we look at the moment. It's a part of scattering matrix, a squared of transmission matrix, but it can be a Hamiltonian Hermitian matrix in case of random quantum dot. In any case, the question and answer of random matrix theory is the statistics of eigenvalues. I could also think of eigenvectors, but the main problem, main peculiarity of random matrix theory is statistics of eigenvalues. It is given by a distribution, which I put here, which has a name tag attached to it. It's called Wigner-Dyson distribution. It's just interesting, how did it come about? Wigner and Dyson were American physicists which have been employed to do atomic bomb, to work in atomic problem. And their part of the project was exploration of different nuclear reactions. There are so many nuclear natures, so many cases, so many experimental data. It's supposed to be very important for the project, that this gentleman got completely frustrated. And they have come with an idea which sounded as a joke by this time. Namely, they say that interaction in nuclear physics are so peculiar and nuclei are so various that it doesn't make sense to look at the details of the interaction. And a good move would be to assume that this interaction is completely random. Okay? So let us just take a random matrix, which is a Hamiltonian of a nucleus, which has some levels. Let us try to understand it, understand my symmetrical problem of eigenvalues in a random matrix. So here we are. So we have many eigenvalues with I choose energies for this. So the different distribution of different energies. Right. And the main point of Wigner-Dyson statistics is that these levels do not want to come close to each other. Look, if two levels are the same, it would give 0 here, no probability. It can be seen as a repulsion of levels. Right. Physical analogy would be a gas of whatever particles which are put into a line, right? And particles repel each other according to logarithmic law. Yeah? Probability for classical system is exponent of energy, total energy of the configuration divided kBT. And to get power law in probability, one needs to have log in the potential energy of interaction between two particles. Good, so these particles repel each other and eventually they try to go out of each other to fill the whole axis. That's not realistic. The eigenvalues have to be cannot go to infinity. To this end, confining potential is added to this distribution, right? So there are some other forces which try to confine these levels, but they repel to each other. So there is some equilibrium between confinement and repulsion, which occurs in the system. Right. And that is such ordering would be different at different temperatures, and kind of a good part of this Wigner-Dyson joke that there is a temperature, inverse temperature, beta stands for 1 kBT, which is takes discrete values corresponding to different types, or how they put it, ensembles of the matrices. Right, there are 3 ensembles. Orthogonal ensemble is for symmetric matrices. Unitary ensemble is for usual Hermitian conjugated matrices. And for strong spin orbit interactions, there is another ensemble which is called symplectic. Let us look at this picture. we will see how levels repel and how ordering of the levels emerge upon changing the ensemble. Here, what I did, I just put the levels in random. Well, that would be a naive idea. Random matrices by their levels is not random. Okay, as you see, some levels come very close to each other, but there are also large spacings between the levels, just because they're random. Let's get to Saginaw Ensemble. And you see immediately that the levels is a little bit more ordered. The probability to come close to each other is smaller. Unitary ensemble, yet smaller. It still looks disordered, but the spacings become more regular. Symplectic ensemble, well, you see eventually very little fluctuations in the system of levels. If you compare it with precise equidistant levels, and there's rather small difference. So, randomness in matrices eventually leads to rather ordered eigenvalues. This is expressed by two words: spectral rigidity. So, to this end, one takes a strip in this level distribution, which encompasses n levels in average, and looks at the variation of a number of levels. And one sees that this variation, it is inversely proportional to inverse temperature, so it's proportional to temperature as all thermal fluctuations. So it is of the order of 1, roughly. Pi squared is of the order of 1. And it decreases from orthogonal to symplectic ensemble. And it becomes 0, of course, for equidistant levels. Okay, a rather complex but still a relevant control question. What is the variation of number of particles for completely random levels? This is something that you know, perhaps you don't remember it right away. Any ideas? Come on, you know this. You certainly talk about this when, for instance, talking about measurements, about collecting the data, estimating the experimental errors. Yeah, Timo, it's a good suggestion, but this is for relative variance. Relative. when you divide variance by number of trials. The formula which I wanted is the following: fluctuation of n squared is just average n. When you take square root and divide by n, you get indeed inverse square root, which you use when you talk about, when we discuss measurements. Kind of each measurement comes with error. To make this error smaller, one repeats measurements many, many times, and inverse square root of n just gives a proper scaling. Good. So for this ensemble, variance is proportional to the n, to the number of levels confined. Let us see. Do I have time for a story about spectral rigidity? Let me postpone it till quantum dot lecture. Good. Now let us apply all these concepts to transmission eigenvalues. So as we remember, any nanostructure can be characterized by a set of transmission transmission coefficients, which are eigenvalues of the transmission matrix squared. Fine. Right, so if we have a nanostructure with big number of channels, we have many these T's distributed like this. The matrix also becomes random, encompassing many channels. So we expect something which resembles Wigner-Dyson distribution. Strictly speaking, the concrete distribution depends on nanostructure time, but fortunately, it is qualitatively similar, and it has a signature of Wigner-Dyson distribution, repulsion of the levels which come close to each other. Here, there's one of the answers which can be obtained exactly. This is for chaotic cavity when we have NL channels in one conductor and R in another quantum point contact. And this is distribution of transmission eigenvalues, right? This parameter beta enters. It depends on the ensemble. Roughly, if we look at zero magnetic field, we are in orthogonal ensemble. If we apply magnetic field, we are in unitary ensemble. And if spin-orbit interaction is strong, we are in symplectic ensemble. Fine. What's the simplest conclusion? Let us estimate conductance fluctuations. Conductance fluctuations is just a sum of transmission coefficients, and the variance is just correlation, comes from correlation of these transmission coefficients. So from the distribution from Wigner-Dyson statistics, right? And what would be kind of simple model? We could say that conductance is again number of eigenvalues in a strip of the order of 1. And then we can relate this estimation to the property we have discussed to spectral rigidity. So variance of conductance would be just GQ squared, and variance of number of eigenvalues in a certain strip. So it doesn't depend on strip. This Dyson distribution tells us is just constant, which means the variance is constant. It doesn't depend on number of channels. Although, if we naively assume that these eigenvalues are random, we would get much bigger variance. Okay, it's not applied. So we obtained this estimation, which we could make considering trajectories. We have obtained it in the language of random matrices. Good. The same concepts can be applied to weak localization. It is a bit more involved. It's not fluctuation of the levels. It's how discreteness of levels affects their usual density. Weak localization is a leading correction to this. There is a corresponding formula which shows that weak localization cancels for unitary ensemble. So it does not persist in magnetic field. For orthogonal and symplectic ensemble, we have opposite signs of this correction, which correspond to this localization or anti-localization. Anti-localization works in the case of strong spin-orbit interaction. Right. There is a concrete formula for chaotic cavity. I would use 2 minutes to talk at least about this transparency. Let me talk about localization, weak and strong localization in 1D. So now our nanostructure is now rather long wire, and we are measuring the conductance and resistance of this wire versus its length. Right. What do you expect? You expect Ohm's law, conductance, which is some constant, divided by the length. If you start with a large conductance and increase the length, sooner or later, the conductance will become of the order of GQ. And our intuition, elaborated in the course of this lecture, tells us that something should happen here. The conductance is already so small that it's only a single channel which provides it. Right? And indeed, our intuition is correct. And in fact, if one plots the actual conductance for long one-dimensional wire, their temperature versus classical conductance or inverse length, one says the following. At large conductances, we have Ohm's law, which is red line, minus small deviation, weak localization correction of the order of GQ. When it goes down, length increases, we have almost no conductance in this wire. It grows exponentially as a length at some localization length. All right. Eventually, it is much smaller than classical estimation. What does it mean? It means that all electron wave functions are localized here at the localization length. And what is the localization length? One can quickly estimate it as a length at which conductance of this wire is of the order of conductance quantum. So for any wire which looks pure and highly conducting, if one takes very long lengths, wave functions will be localized. This is a bit difficult to see because quantum mechanics doesn't hold at this long scale, and due to finite temperature, there's dephasing, quantum mechanics doesn't work, and there is some conductance, but that conductance will be already temperature dependent and things like that. Good. I have yet a couple of transparencies, which is about 2D and 3D. There's difference in manifestations of localization and higher dimensions. But I'm out of time, sir. I guess I would stop here. Thank you for your attention. I stop the recording.